Good evening, everyone. In this video, we will continue with the system design decisions. Okay, we'll be looking at two of these aspects: identifying concurrency and allocation of subsystems. Let's look at them. So, in the analysis model, of course, as in the real world and in hardware, all objects are concurrent. Okay, so all the objects are concurrent. However, in an implementation, not all software objects are concurrent because, like, you will be putting several of these objects into a single processor. So one processor may support many objects. Okay. So in practice, you can actually implement many objects on a single processor if the objects cannot be active together. Okay. See, if you are running several objects in a single processor, that means like you are executing them in some order. Okay. So that means like the objects are not active together. Okay. Then only you can be able to run these multiple objects onto a single processor. So one important goal of the system design is to identify the objects that must be active concurrently and the objects that have mutually exclusive activity. So which run in concurrently, that means like they run parallelly, and then like the objects that have mutually exclusive activity. We can actually fold like mutually exclusive objects onto a single thread or a task. Okay, so that's about identifying the concurrency. State model is actually the guide for identifying the concurrency. Two objects are inherently concurrent if they can receive events at the same time without interacting. Okay. Say for example, like if you are considering an airplane, so the engine and wing controls are actually working concurrently. They should be working together, isn't it? So these objects are actually okay. So they are working together. Okay. But in general, whenever you are designing a system, actually independent subsystems are designable. Okay. If you have independent subsystems, then we can actually assign them onto different hardware units without any communication cost. Okay. So these individual subsystems can be running on different hardware units. Okay. And they will be working independently, and you don't have to basically have any communication associated. I mean, like you don't need any communication between these subsystems. Okay. Of course, like this is what we are actually doing in the operating systems, isn't it? We can actually simulate logical concurrency in a uniprocessor with hardware interrupts, operating systems, and multitasking mechanism. Okay, you can still achieve on a single processor the concurrency, but then like most often, like if you want to achieve concurrency, okay, so it is better that they will be okay, so they should be completely independent, and then like the subsystem should be independent, and then like they are running on different hardware units. When you are trying to define these concurrent tasks, although all objects are conceptually concurrent, in practice many objects in the system are independent. Okay, this is also one important thing to remember. Okay, so during the analysis, like almost all the objects are concurrent. Okay, so although these objects are conceptually concurrent, in practice many objects in a system are actually independent. By examining the state diagrams of individual objects and the events that they are actually exchanging among them, you can actually fold many of these objects into a single thread of control. A thread of control is actually a path through these, then a path through these set of state diagrams on which like only a single object at a time is active. So you are in the state diagram of one of these objects. Okay, the thread control is actually going there. And say, for example, if this object actually sends an event to another object, the thread controller actually passes to the received object. So in that sense, like a thread of control is a path through this set of state diagrams. Okay. In terms of ATM example, okay, if we really look at, say for example, whenever the bank is verifying a transaction or like the customer or something, the ATM is actually idle, isn't it? So it is actually waiting for that particular transaction to finish. Okay, so then we can actually combine ATM and bank transaction objects as a single task, and you can put it on a single processor because like there is no concurrency associated there. Okay, that's about defining these concurrent tasks and then like concurrent subsystems, how they should be. I mean, which of the subsystems are actually concurrent, or like which are actually mutually exclusive. Once you have actually identified which of these subsystems are concurrent, you can actually allocate them, okay, allocate these subsystems to different hardware units, okay. So we can allocate these concurrent subsystems to a hardware unit by following several decisions, okay. So we have to estimate the hardware resource requirements for that particular subsystem, okay. And then like we also have to make hardware software trade-offs, okay, whether to run it in hardware or software. We will discuss all these things in detail, okay, in the and we also okay, so we also can allocate these tasks or subsystems to processors to satisfy performance needs and also minimize inter-process communication, okay, inter-process communication. So that means like if you are, I already mentioned it, okay, so if you basically run the subsystems across multiple nodes, multiple hardware, okay, what is happening to the inter-process communication? So we will discuss these things. And we should also determine the physical connectivity of units that are actually implementing these subsystems, okay. So let us look at these four things one after the other. So the first thing is estimating the hardware resource requirements. The number of processors that are actually required for running a particular subsystem depends on the volume of computations and the speed of the machine. Okay. So assume like say for example, if we consider our ATM case, okay, you don't need that much of processing, which we have already estimated in terms of the performance already. Okay. But then like if you think about a military radar system that actually generates too much of data in too short a time and to handle in a single CPU. You cannot handle them in a single CPU. A lot of data is generated very quickly and you have to process it very quickly so that like you can actually identify any threats or something. So in such a case, like many parallel machines must digest the data. So that means like you need to have multiple CPUs there. Of course, as I discussed, like in the ATM case, you really don't need multiple CPUs for the ATMs. Okay, remember that. For the ATM, you need a simple CPU. That is okay, fine. So basically, to decide this one, this estimation, okay, the hardware resource requirements, you have to basically consider both the steady state load and the peak load. Okay, both are important. So the steady state we have actually calculated for this ATM example earlier. Okay, we have actually thought like, okay, so approximately there are around 40 different branches. That means like there are 40 different ATMs existing. And assume like each person takes a minute to execute a single transaction. So that means like approximately like you have 60 transactions per minute. Each transaction needs a second, okay, a transaction per second. And the time for processing a transaction, we also know. So then the steady state load, you can actually calculate by multiplying the transactions per second and the time for processing a single transaction. So with that example, what we have considered is like we said like the transactions per second is 1 and then like time for processing is 60, okay, which is minutes. So that means your steady state load is 60, okay, based on our approximation, okay. You don't have to be exact, okay, so you are trying to estimate, okay, in this case. Of course, peak load is also very important. Of course, we have seen with the ATM example, it cannot go beyond that one, okay. So but of course, like if you really look at all these subsystems of ATM, the way like in the last video, like I have shown you, like the ATM is there, the consortium computer is there, and the banks are there. The consortium computer may become like a bottleneck because like multiple ATMs are basically sending the transactions to the consortium computer, which is actually routing them to the multiple banks. Okay, so this consortium computer, because like it is actually receiving like almost 60 concurrent requests, okay, at any time, okay, based on the steady state load. So you may need this multiple CPUs for this sort of consortium computer, which is lying in the middle. Okay, if you really remember the diagram which we have seen in one of the earlier videos about the ATM subsystems. So that's about the estimating hardware resource requirements. Okay. Once you basically estimate that one, you should also make these hardware software trade-offs. Okay. You must decide which of the subsystems will be implemented in hardware or whether it is in software. There can be several reasons for implementing subsystems in hardware. One of them could be cost. Say for example, if your existing hardware already provides exactly the functionality required, then great, like you basically execute it there. But of course, like say for example, assume like you have to do a lot of floating point calculations. Okay, implementing it in software would be like pretty much expensive. Okay, it is rather very easy to buy a floating point chip. Okay, but of course, like it has its own cost associated with this one. Okay, which of them you will take? There should be a trade-off for the thing. So there is also another aspect, the performance. The system may actually require like higher performance than the general purpose CPU may provide. There can be situations where like your application may require that one. Assume like say for example, if your application is actually it is about gaming application, so then you may need to do a lot of graphics rendering, graphics processing, and similarly like if it requires a lot of video processing. So doing it on CPU would be really bad. I mean, like today we have these GPUs, graphic processing units, which actually provide you better performance in dealing with these graphics and video rendering. So then for your application, like those sort of subsystems which actually deal with that particular processing, you will be running them on that particular hardware. Okay. So these sort of design decisions are to be taken care of. Okay, in the system design. Then once we have identified these things, we have to allocate these tasks to the processors. Okay, so that is like allocating these software subsystems to the processors. There can be several reasons for assigning tasks to the particular process. One of them can be logistics. Certain tasks are actually required at specified physical locations to actually control the hardware or permit independent operation. Think again about our same ATM case. Okay, so in general, what is happening is like you are actually putting certain information and then like you are waiting for the transaction to finish and you are basically getting the money. What happens if there is a communication error in the middle of the transaction? How do you deal with this? There can be several ways of handling it. You can basically very simply say like, okay, so if there is a communication error happens even during the middle of the transaction, you can actually cancel it. Alternatively, you can say like, okay, so there you will not allow more functionality, but then like you will allow a limited amount of functionality. Okay. Say for example, when there is communication error, okay, so the user can still do certain things, something like say for example, he can change his PIN number on the ATM card or something like that one. So you will not allow him to do all the transactions, but certain transactions you may allow. So if you don't allow any of these transactions, then the ATM can be a simple terminal for just like a traditional Unix or Linux-based system. So it can be simply a terminal. So all the processing is happening somewhere on a different machine. Say for example, in this case, on this consortium computer. Okay, and then like the ATM is just a terminal there. Alternatively, if we allow some sub transactions to be running, then you need a CPU in the ATM itself. So these are some of the reasons why you would allocate certain tasks to certain processors. So these are all part of the design decisions. Then you should be worried about communication limits as well. Okay, say for example, if during the subsystems have to communicate a lot and they have to basically exchange a lot of data, then you should also worry about the bandwidth between these subsystems. Then where you actually execute these processes, it is also critical. Okay, so if a lot of communication has to happen, then it is better that you should run them on the same processor. So this is the same thing which you will consider in terms of the computation limit as well. Assign highly interactive systems to the same processor. That way, like the systems, subsystems will be running really faster. Okay, this in turn reduces this sort of communication costs as well. Okay, of course, like if you have the independent systems, then run them on separate processors. Okay, so all these design decisions are to be considered. We also have to actually determine the physical connectivity. Say for example, determining the arrangement and form of the connections among these physical units. Different subsystems are now running on different units. Okay, so you have to decide on the connection topology. Choose a topology for connecting the physical units. Okay, say for example, like in the ATM case, we already have discussed. Okay, that now they are actually connected through star topology, isn't it? So basically like the ATMs are existing, okay, and then like the consortium computer, and then like there are multiple banks. The consortium computer is the one like which is actually facilitating the communication across the ATMs. Okay, so ATMs are actually communicating with this consortium computer, and the consortium computer is the one which is actually communicating with all the banks. So that's a star topology, with the consortium computer becoming the master. So for any system like which you are trying to develop, you need to basically choose that particular topology for all the physical units which are part of the system and all the subsystems which are running on these different physical units. So associations in class model actually often correspond to this sort of physical connections. Okay, associations are a good point where you can actually see like where the physical connections are. Similarly, like the client-server relationships among these subsystems is also a good place to see like how to establish this sort of connection topology. This again, like we have discussed in the previous video when we are talking about different layers and then like those things. Okay, different layers, how these layers were actually interacting of subsystems. So there can also be repeated units. Okay, so there also like you have to choose the topology for the repeated units. Say for example, I gave a simplest example of the ATM case. So the consortium computer, okay, it may have to support a lot of load. So you can have multiple CPUs. So that means like you have multiple repeated units there for the consortium computer. Then what is the sort of topology you will basically put? Okay, so it is not a single machine that is decided. So how do you basically have multiple CPUs which actually can process this load which is coming to this sort of consortium computer? So there are a lot of concepts like load balancers, etc. Okay, which is beyond this current discussion. Okay, but then like so you can actually put a load balancer and then like the requests are coming, the request can be routed to multiple these consortium computers which actually can handle connections to multiple banks. Okay. So if you want to know more, so load balancer is the keyword, and then like you can check about that one. So then we should also think about this sort of communications. Okay, so we also have to choose the form of connection channels and communication protocols that should be existing. Okay, say for example, the interactions between the subsystems can be synchronous. Okay, and synchronous and blocking. Okay, and asynchronous. Okay, so we have already seen when we were checking these sort of sequence diagrams. Okay, so synchronous things like you will basically send the request and immediately you will get the response. You will wait till the response. Asynchronous is like you will send the request and eventually it will come back the response. The blocking will be a different form of synchronous where like you will not wait for it immediately, but then like you will be regularly checking. Okay, and your call is actually blocked until the response basically comes. Okay, that's about different forms of interactions. Similarly, we also have to estimate the bandwidth and latency of the communication channels as well. Okay, so these are all the design decisions which you should be looking at. And based on these decisions, okay, and based on the concurrencies of the subsystems which you have identified, you will be putting those subsystems onto that particular physical hardware. Okay. So regarding the references are concerned, we are still in chapter 14 of object-oriented modeling and design with UML. So Michael Blaha and James Rambo. Thank you very much for your attention.